Welcome to today's explainer. If you work in a laboratory, you already know that absolute precision isn't just a nice to have, right? It's literally a fundamental requirement. Well, today, we're demystifying the incredibly meticulous ISO 86556 gravimetric calibration process for volumetric apparatus. We are going to track the actual literal journey of a single drop of liquid from the extreme constraints of the physical lab setup all the way down to the complex mathematical formulas we use for measurement uncertainty. It's going to be fascinating.
Here's our agenda for this journey. First, we'll look at the foundational piston-operated standards. Second, we'll set the stage by covering the strict equipment and lab environment required. Third, we'll walk right through the physical gravimetric procedure itself. Fourth, we'll explore how we actually convert mass to true volume. And finally, we'll tackle the critical measurement uncertainty math.
So let's start with Section 1, Piston-Operated Standards, and the foundation of metrology. Okay, let's dive into this. Piston-operated volumetric apparatuses, things like pipettes, burettes, and dispensers, they are the absolute workhorses of modern laboratories. But relying on these tools to consistently dispense microliters of fluid? That means we have to rely on an incredibly strict set of international standards to ensure they're performing flawlessly every single time. And that brings us to the ISO 8655 series, which governs this whole precise science. It's broken down into some specific parts. Part 1 covers general terminology, Part 2 focuses exclusively on pipettes, while Part 3 covers burettes. But for our explainer today, the real star of the show is ISO 8655-6. This is our ultimate definitive guide for the gravimetric reference measurement procedure, which is essentially the specific method of using a highly calibrated scale to weigh water to determine exact volume.
Moving right along to Section 2, Equipment and Lab Environment, setting the stage for precision.
You see, in gravimetric calibration, the environment itself is just as important as the equipment. You literally cannot just walk into a room and start pipetting. First off, your test liquid has to be distilled or deionized water that meets ISO 3696 Class 3 standards. The room has to be totally draft-free, with relative humidity carefully controlled between 45 and 80% because we have to prevent rapid evaporation. The temperature? It must be stabilized at exactly 20 degrees Celsius, give or take 3 degrees, and it can't fluctuate more than half a degree per hour during your test. I mean, just think about that. Even a slight draft could ruin the whole thing. And perhaps the most uncompromising rule of all? Both your equipment and your test liquid have to sit in this exact environment for a mandatory 2-hour acclimatization period before you even squeeze out a single drop.
Now, what's really interesting about this slide is that you can't just use any old lab scale for this either. According to Table 1 of the standard, your analytical balance's resolution has to scale perfectly with your target volume. If you're calibrating a small volume, let's say under 20 microliters, you need a staggering resolution of 0.001 milligrams. That is unbelievably sensitive. We are basically talking about measuring the weight of a microscopic dust speck. The parameters are so tight that the expanded uncertainty of the balance must be less than 1/4 of the maximum permissible systematic error of the device you're testing.
All right, Section 3, the gravimetric procedure, the physical journey of the drop.
Let's walk through the literal, physical action of dispensing this test liquid. It is a highly choreographed routine, completely designed to eliminate any micro errors. First, you have to pre-wet the pipette tip exactly 5 times. Why? Well, this establishes a critical humidity equilibrium inside the dead air volume of the piston. Then, immerse the tip perfectly vertically into the water. And the standard dictates the exact depth, only 1 to 6 millimeters depending on the volume. After drawing the liquid, you wait a mandatory pause time of 1 to 3 seconds, just for the fluid to settle. Finally, when you're dispensing into the weighing vessel, you have to touch the tip against the interior wall at a very precise 30 to 45 degree angle, drawing it up slightly to remove any lingering fluid.
And you don't just do this once. No way. This meticulous physical process is repeated 10 separate times for a single test volume. But wait, there's more. You also have to test across the device's entire range. The standard requires testing at 3 specific volume points: 100% of the nominal volume, 50%, and then either 10% of the nominal volume or the lower limit of the usable range, whichever one is greater. So 10 drops per volume, 3 volumes. That is a whole lot of perfectly angled, perfectly timed drops, right?
Section 4, Mass to Volume Conversion. This is where the physical work ends and the metrologist's math begins. So, you've got your mass readings from the scale, but here's the catch. Raw mass does not perfectly equal true volume. Now, you might be wondering, why doesn't a microdrop's weight just perfectly match its volume on a scale? Well, it's because a microdrop's weight is heavily influenced by the surrounding environment. To find the actual volume, we have to apply what's called the z-factor. This is a brilliant mathematical correction factor used to convert the raw mass of our distilled water into the true volume. It does this by accounting for some unavoidable physical realities: the changing density of water, the buoyancy of the air physically pushing up on our sample, and even the thermal expansion of the pipette itself.
And this brilliantly illustrates the exact mathematical formula from the ISO standards that makes this mass-to-volume conversion possible. I know it might look a bit intimidating at first glance, but really, it's simply a ratio balancing the physical forces at play during the exact moment you took your measurement.
Let's just break these variables down conversationally. The formula relies on water density, which is noted as ρW. We calculate that using the Tanaka formula to adjust for temperature. Then we have air density, ρA, calculated using the CIPM formula, which neatly factors in barometric pressure and humidity. We also have to factor in ρB, which is the reference mass density of the weights used to calibrate the balance itself. That's typically around 8,000 kilograms per cubic meter. And finally, gamma. This represents the cubic expansion coefficient of the pipette's specific material. Because believe it or not, even the plastic or glass of the device is slightly expanding or contracting depending on the room temperature.
Let's move to and see how this all builds into Section 5, Measurement Uncertainty, proving the work via ISO TR 20461. So the crucial point here is understanding the two distinct types of errors we're actually evaluating. First, we have systematic error. This is essentially your bias. It's the difference between your target volume and the average volume of your 10 dispensed drops. Basically, it shows how consistently off the device is from the true mark. Random error, on the other hand, is the experimental standard deviation, the spread, of those 10 drops. It shows the true repeatability of the pipetting process itself. And of course, both of these must fall within strict tolerance limits.
But to truly state our final expanded uncertainty, we have to look way beyond just those 10 drops and start factoring in type B uncertainty contributors. These are the hidden variables. We're talking about things like the microscopic drift of the analytical balance over time, or liquid evaporation, which, by the way, is absolutely critical if you're dispensing volumes under 50 microliters. If you don't use a vapor trap or calculate the mass loss through evaporation, your data is completely compromised. Actually, scratch that. It's not just compromised. Ignoring any single one of these factors, like tiny fluctuations in water temperature or that material expansion we talked about, can literally invalidate an entire laboratory workflow. Your lab's data could be fundamentally flawed if left unaccounted for.
Which brings us to our final thought for this explainer. Just look at the immense, uncompromising rigor required by ISO 8655-6 and ISO TR 2461. From the mandatory 2-hour acclimatization to the exact 30-degree dispensing angle, all the way to the CPM air buoyancy math. It really begs the question, is your lab truly accounting for every single micro drop of uncertainty? Thank you so much for joining me on the journey of a drop today. Keep learning, keep questioning, and keep your calibrations precise.